Hi, I'm Jen Mu of Cadence Design Systems. Welcome to Sigrity Tech Tips. Today, we bring you another installment of how to build and verify your multi-gigabit serial link to meet industry compliance standards. Our video today will show you how to perform full-wave 3D extraction, making sure you have the right slice of the design before you invest considerable time and energy in the actual extraction. Using this methodology, you can avoid wasting hours on a full-wave 3D extraction where critical circuit elements are missing, making the results unusable. This methodology is an important step in multi-gigabit serial link compliance, and one that can be performed by not only 3D analysis experts, but also opens up 3D extraction to design engineers responsible for the PCB or IC package design. With a small investment of time up front, you can be confident that even on your first time, your 3D extraction will yield the results you desire. With added accessibility to accurate 3D extraction, you can be confident that your schedule milestones will be met and your design cycle time will be predictable. In today's video, you will see us utilize the Allegro Sigrity SI base and the system's serial link analysis option. To learn more about these products, visit us at www.cadence.com. Now, I will turn it over to my colleague, Brad Brim.
Thank you, Jen, for the introduction. Again, my name is Brad Brim, product engineer in the Sigrity team at Cadence Design Systems. I've been involved with high-frequency EM modeling tools for many years and always believed in applying multiple tools to accomplish my modeling tasks, from abstract circuit simulation to detailed 3D EM analysis. Too often we think we should only apply the most detailed and computationally expensive tool for all our modeling tasks. This wastes time, both computer time and engineering time. Today, I will expand on a previous Sigrity tech tip by my colleague Charlie Shih on the topic of cut and stitch EM simulation flow. This flow was initially implemented as an automated approach to 3D EM simulation. I'll discuss and demo how this same flow can apply hybrid solver technology to yield essentially the same results while saving significant time, both computer time and engineering time. As a review, the Sigrity 3D EM cut and stitch flow requires a polygon boundary to define the area for local 3D simulation. This region is then partitioned into zones by simply drawing cut lines. The layout is not changed, only the 3D cut boundary and zone lines are defined. Then the automated flow performs 3D simulation for each zone, and those individual results are combined by circuit simulation for a composite result. Though it's applied much less often than it could or should be, there's an option to uniquely select either the 3D solver or the hybrid solver for each zone. A hybrid solver is a very efficient, though approximate, combination of circuit simulation and EM analysis. A hybrid solver is much faster and requires much less memory than a 3D solver, yet for many designs yields highly accurate results. With little or no experience, you can reliably select which zones to specify for detailed 3D analysis and which to simulate with the hybrid solver. Let's examine the benefits of a mixed solver cut and stitch flow using a PCB serial interconnect. This simulation is for a very long diff pair from one mounted component to another, including multi-layer transitions at each end and in the middle. 7 zones were defined that isolate the 3D transition regions from the more uniform routing area. The 4 routing areas were simulated very effectively using the hybrid solver, and the 3 multi-layer transition areas simulated with the 3D solver. This interconnect is very long electrically, with each impedance ripple in the response corresponding to a half wavelength, nearly 14 wavelengths at 20 gigahertz. Even without the complexity of multi-layer transitions, this is a big simulation. It took over 9 hours to complete the 3D simulation of this full design. When the cut and stitch flow is applied and all 7 zones are simulated with the 3D solver, the time is cut in half to about 4.5 hours. The time savings is great, but an even more significant reduction in memory occurs. When we apply the hybrid solver to the 4 uniform routing areas, the computation time reduces to less than 1 hour. That's an order of magnitude reduction in simulation time to achieve the same level of accuracy as a 3D EM simulation of the full design. And the only insight required was to recognize the hybrid solver can be applied to uniform routing regions. We simply select the relevant solver for each zone prior to simulation. An IC package SerDes channel was selected as an example. It contains 2 diff pair interconnects and transitions to both chip and board. Before jumping into details of the design, let's first examine the multi-solver simulation flow applied in the demo. Step 1. Start with the full design layout. Disable all but the few signal nets of interest. Keep the full power delivery network. Step 2. Perform a hybrid solver simulation with the full PDN. This establishes baseline for comparison when you cut the PDN for local simulation in the next step. Step 3. Perform a hybrid solver simulation of the cut design and compare with the full PDN results. If these results compare well, then you're certain you haven't excluded PDN effects, such as a resonance, or that you haven't cut away too much of the design to get good local simulation results. Step 4. Perform a mixed solver cut and stitch simulation. Define zones to partition 3D versus uniform routing areas. Then select the appropriate solver for each zone and launch the simulation. Step 5. As an optional verification step, you can choose more zones to be simulated by 3D. In the extreme, you can select all zones to be simulated by 3D, which is the original single solver cut and stitch flow. Step 6. As a final verification, you can even pursue a 3D simulation of the entire cut design. Now, let's preview these simulation steps for the example design. We'll jump directly to step 2 with the full PDN and 2 diff pairs selected. Ports are set up and a 20 gigahertz bandwidth defined. The hybrid solver simulation completes in only 6 minutes. Again, this provides a baseline to judge results for the cut design. Step 3. Quickly cut the design with a rectangular window and launch another hybrid solver simulation. This time the simulation completes in less than 20 seconds. The results compare well and allow me to cut the design further with an arbitrary polygon and quickly test. I have both avoided issues and I get a more efficient 3D simulation. Step 4. Change to the 3D EM workflow and set up for cut and stitch simulation. I draw 2 cut lines to define 3 zones. 1 zone at the chip transition, 1 at the board transition, and 1 for the strip line routing area. I had initially intended to select the chip transition for 3D simulation, but the hybrid solver results showed the board transition dominates circuit performance over the entire bandwidth. Therefore, I chose only the board transition for 3D simulation and stayed with hybrid solver simulation for the die transition and interconnect zones. The cut and stitch simulation completes in about 13 minutes, with only seconds required for the 2 hybrid solver zones. Step 5. As an optional verification, I select all zones for 3D simulation. The simulation takes about 12 minutes for the die transition and 27 minutes for the interconnect. With the 13 minutes required for the board transition, that's a total of about 52 minutes. The previous mixed solver results compare well with these new all 3D results. Step 6. Only as a computational resource comparison, I perform a 3D simulation of the entire cut design. This simulation required about 66 minutes to complete and about twice the memory of the all 3D cut and stitch simulation. The results are extremely close to the all 3D cut and stitch results. Now, let's proceed to the demo. Step 1 of selecting signal nets and their relevant power nets was completed before the demo, and the design brought into the PowerSI GUI for hybrid solver simulation. Therefore, we begin the demo at step 2. We have 2 differential pairs, TX in yellow, RX in pink, and the blue net is the ground net. The ground net is a solid plane on layers immediately above and below this routing layer, except for the die transition region. Let's first look at a 3D view of the die transition region. You can see that I have return paths, but they're far from ideal. And that's the reason that this design was being considered for 3D simulation. Let's then go back and look at a 3D view of the board side transition. What you'll see is that we have fairly standard transitions. We have a large solder ball pad, interlayer transitions with vias, and then we have escape routing. Let's close the 3D view and return to the layout, and let's look at the 8 ports that I have defined. Ports 1 through 4 are defined actually on the bottom layer. for the TX and RX respectively. Ports 5 through 8 are defined at the die side on the top layer. All ports reference single balls or single bumps for their return paths. Let's now look at the frequency sweep. I have defined a sweep from 100 megahertz to 20 gigahertz. Since we're going to use all default simulation parameters, I simply need to go to the PowerSI workflow for extraction and launch the simulation. During the simulation, we're going to pause, and I will also set up for a differential channel results display. We're back after about a 6-minute hybrid solver simulation of the channels and the full PDN. I've set up a display of the differential mode S parameters. The TX traces are blue and the RX traces are red. We'll maintain this consistently throughout the demo. Notice very low reflection or return loss at low frequencies for both TX and RX, with significant reflection at higher frequencies. Also notice fairly low insertion loss over the entire band. Both reflection and transmission show impedance ripples, which are due to die side and board side parasitics, as well as trace impedance differences versus expected values. Let's examine the phase of the S parameters. There are 3 unique sets of phase behaviors. The board side reflections have very little phase accumulation, and the die side reflections have large phase. Notice the through phase is about half the die side reflection phase. Also, the RX phase is always greater than the TX phase, which makes sense because the RX channel is physically longer. But before we go to the next step of local simulation for the cut design, let's consider what these results tell us already. The phase behaviors tell us the reflection occurs dominantly, if not entirely, at the board side transition over the entire bandwidth. Since the board side reflection phase starts at about -90 degrees and decreases slowly with frequency, we know this transition is highly capacitive and localized to the board side transition. We're now at step 3 in our multi-solver simulation flow, hybrid solver local simulation of the cut design. To start with, I'll cut the design quickly with a simple rectangle. We can worry later about crafting just the right 3D simulation region. First, we want to assure we aren't ignoring any PDN resonances or cutting away too much of the design for our local simulation. Edit, cut by area, and I simply draw a local rectangle around my design of interest. I say cut outside to keep only what's inside of the rectangle. It performs the cut, and then I launch a database cleanup stage called shape processing. It'll return in just a second and show me only what's inside of the rectangle. It's all set up with ports. The frequency sweep is already defined, and just like last time, I go to the PowerSI workflow and I simply launch the simulation. While the simulation proceeds, we'll pause and I'll again set up the results display. The simulation completes quickly, in about 20 seconds. Most of the pause was to set up plots to compare the previous full PDN results with the present cut PDN results. The full PDN results are displayed as dashed lines. Notice the exact comparison between the 2 sets of data. This means we haven't ignored any PDN effects and that we have more than enough of the PDN to represent local return paths. This is valuable information. Too often we get hours into a 3D analysis only to realize we aren't simulating enough of the design. This is a frustrating waste of engineering time we can avoid with only a few minutes of upfront hybrid solver simulation. We're now at step 4, which is mixed solver cut and stitch simulation. To save time in the demo, I took a few minutes offline to set up most of the analysis, but we'll review before launching the simulation. First, I crafted a more conformal cut region for the local simulation. I verified it maintains the same level of correlation we observed for the quick and dirty rectangular cut. Then, I set up 3 zones by defining 2 cut lines. Notice Zone 1 at the top is for the board side transition, Zone 3 for routing, and Zone 4 for the die side transition. For the demo, I'll define a new cut line to split the routing zone and then back out that change. In the 3D EM workflow, I cut on split cutting polygons. A new window opens to manage zones and the solver for each zone. Notice the cursor now indicates cut mode. I draw a new cut line to split zone 3 by clicking and dragging. When I release, I split the cutting polygon. Notice zone 3 is replaced by 2 new zones. As you can see, defining zones is quite easy. To undo this change, I can select the 2 new zones and merge them. I'm back to where I was. Before closing this window, I'll select the solver for each zone. Notice all zones are initially set to 3D because cut and stitch is part of the 3D workflow. We know from the hybrid solver results the board side transition dominates performance. Therefore, I'll select the hybrid solver for both routing and die side zones and apply the 3D solver only for the board side zone. The next step is to generate speed files, which are Sigrity design databases. The present design file is not changed, but a new file is created for each zone. When I launch the simulation, these files are simulated with the selected solver in a subdirectory of the present zone. There's no need to check these new files for this simple of a design. Now, I'm ready to launch the simulation. The GUI asks if I want to use the cut and stitch flow. If I decline, it simply ignores the zones and performs a 3D simulation of the entire design. As before, we'll pause while the simulation is performed and I set up display of the results. The simulation completes in about 14 minutes. 3D simulation of the board side transition requires about 13 minutes, and hybrid simulations of the other 2 zones take about 10 seconds each. The solid traces are the cut and stitch results, and the dashed traces are the previous hybrid solver results. I've displayed the board side reflections only to unclutter the plot. Notice the cut and stitch reflections are smaller at higher frequencies. The phase of the S parameters are also very similar between the 2 results. This implies the hybrid solver was overestimating the capacitive parasitics at the board side. Though this overestimation is only about 10%, it's the dominant effect in the channel, so it's good that we applied 3D simulation for it. We're now at steps 5 and 6 of our mixed solver simulation flow. This is the verification stage. For step 4, we chose to apply cut and stitch with 3D applied only for the board side zone. Was that sufficient? With a bit of experience, you'll know the right answer, but for now, you probably have no clue. For step 5, 3D cut and stitch, I can simply change all zones to be 3D, configure their speed files to be regenerated, and simulations performed again. Then, simply relaunch the simulation. This is essentially the same thing we did for step 4. Follow along as I set up for 3D cut and stitch. First, we open the Split Cutting Polygons window. I select the 2 zones that I previously performed by hybrid solver, and I configure those to be performed by 3D solver. For the board side zone, I previously simulated by 3D, so I don't need to regenerate the speed file or do the simulation again. I can reuse those results. I regenerate the speed files. As before, no need to check the speed files for a design this simple. Now, I simply relaunch the simulation. And I accept the cut and stitch flow. Again, we'll pause during simulation while I set up the results display. For step 6, I won't demo the analysis setup, but while paused, I'll perform the analysis. Recall that we've twice seen the prompt asking if we want to perform cut and stitch. With literally no setup changes, I simply relaunch the simulation and decline cut and stitch in order to perform a full region 3D simulation. The 3D cut and stitch simulation completes in about 52 minutes, less if the previous 3D results for the board side zone are reused. The 3D simulation times are about 12 minutes for the die side transition and 27 minutes for the strip line routing. The full region 3D simulation completes in about 66 minutes, but the memory consumption is twice that required by the 3D cut and stitch simulation. The solid lines are multi-solver cut and stitch. The dashed lines are 3D cut and stitch, and the dotted lines are full 3D simulation. As expected, there's very little difference between 3D cut and stitch and full 3D results. Though the agreement between mixed solver cut and stitch versus 3D isn't perfect, it's fairly good. Both the reflection and transmission levels compare well, but the impedance ripples are a bit different. This difference is due mostly to the characteristic impedance variation between hybrid and 3D solvers. Bottom line, our mixed solver cut and stitch results, with only the board side transition done by 3D, were accurate. In this verification part of the multi-solver simulation flow, we've learned how easy it is to apply both hybrid and 3D solvers for cut and stitch. We've also seen how easy it is to verify multi-solver results if you have any accuracy concerns. Most importantly, we've seen how to apply hybrid simulation to understand design performance and assure local 3D simulation success. This completes the demo. I'll now summarize with 2 more slides. We return to the previous slide on mixed solver simulation flow. Applying multiple solvers is a topic that goes well beyond cut and stitch, but it's the focus of this entire simulation approach. It all starts at step 2 with a full design simulation using the hybrid solver, a simulation we could never hope to complete using the 3D solver. Then, in step 3, we quickly validate and even tune our circuit for local simulation success and efficiency. Again, this is something impractical with 3D simulation. Before going to 3D simulation, we can learn a lot from the hybrid solver results. In this case, the board side transition was seen to dominate circuit performance and guided me to select only that zone for 3D simulation. The 13-minute cut and stitch simulation of step 4 provides us with accurate results of this SerDes channel. We can optionally validate this with an all 3D cut and stitch simulation of step 5 or a 3D simulation of the entire cut design of step 6. As we gain experience, we may be tempted to skip the initial 2 hybrid solver steps and go directly to a mixed solver cut and stitch simulation. However, even for the most experienced analyst, these 2 initial steps are a minimal investment for assured success, efficiency, and insight to design performance. They help us to be even more successful with the mixed solver cut and stitch flow. I suggest you seriously consider them for your modeling tasks. The Sigrity cut and stitch simulation flow is driven from a single design file available in a single user interface and enables application of multiple solver technologies in an automated manner. It provides significant time and memory savings and helps to assure accurate results with minimum engineering time investment. The question is not whether to apply 3D EM or hybrid solver technology, but rather how to best apply 3D EM and hybrid solver technology. Thanks for joining me today.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.